Hi everybody. So just now we have done with Ohm's law, and now we are going to start. We are going to study what we call as drift velocity. All right. Before I start drift velocity, what I'm going to tell you is I have a conductor, and we know that conductor has a large number of free charge carrier, that is free electrons. And we know that free electrons are in a continuous movement, right? Free electrons are continuous movement, right? So, however, average velocity of free electrons are under zero. Average velocity of all the free electrons are what we call as zero, right? So, what happens is that if we don't apply electric fields, free electrons are moving, right? And start hitting fixed ions and then come back with the same velocity. So they are in a random motions, right? So free electrons, when they hit the fixed ions, and they come back with the same velocity, but in a different or random direction. So overall, since electrons, huge number of electrons, all the free electrons in a conductors are in continuous movements, but in a random direction. So therefore, the net flow is going to be zero. Therefore, we say that if we don't apply electric fields, alright, the current in a conductor is going to be zero, even though there is a flow of current, flow of charge. I mean, there is a movement of charge because of thermal effect or thermal agitation. Alright, so this is what I have. And so now if I apply electric fields, if I apply a potential difference, what happens is that now electrons are under the influence of electric fields. So they start moving in a direction opposite to the direction of electric field. So you find a net movements. You find You find what we call the average movement of electrons. Average movement of electrons. So therefore we call there is a rate of flow of a charge. Therefore we call there is a net flow of a charge. So this is what I have. Normally there is no flow of a positive charge take place. Positive charge the fixed. Alright. So therefore normally it is electron that normally flow in a conductor. So direction of electron is always opposite to electric fields. Direction of an electron is why? Because electron is negative in nature, right? But positive, here I have shown you a positive movement, but in actual case there is no movement of positive. So how we visualize the movement of positive is that the movement of positive is opposite to the movement of negative charge. If negative charge move in that direction, so we say that positive charge move in opposite direction. This is what we saw. And now we say that I take this cross-section area. When I take this cross-section area, I see the net movements. I see a net movement of charge crossing this cross-section area, and therefore we say there is a net flow of charge. So we find there is a net movement of negative charge across this area. Therefore there is a flow of charge. If you don't apply electric fields, the movement of the negative charge crossing this area is equal to movement of a negative charge crossing opposite direction. So therefore the net movement is going to be zero. Alright. Now, so again this is what I have, right? This is another example, right? This is I take any arbitrary reference plane and I see electrons crossing this area, charge crossing this area. Alright, in a given times, if more charge is crossing this area, the flow is greater. If less charge is crossing this area, the flow is less. So what I'm going to do is I'm trying to build out, right? What we call as build up the concept called drift velocity, right? So this is what we have a movement, right? If I have this is a random, right? This is a random, right? Electron. I take a particular part of a particular electrons, right? So there is a random motions, the random now, alright, the path is in a random, right? So when I apply electric field, there is a net shift. There is a net shift. Alright? Electrons shift in this direction. Electrons shift in these directions. So if I don't apply electric fields, then there is no net shifts, or because it is a randoms. So therefore average is going to be 0. Alright. So now I'm going to do this. So first what I'm going to do is without applying electric fields. First electric field is 0. First I'm not going to apply electric fields. First electric field is 0. So in a conductors I have n number of free charge, right? I have n number of free electrons, and all these n number of free electrons are in a random movements are in a random directions, right? So they move in a random directions, all right? Movements or they moves in a random directions. Random directions. However, so when those electrons hit positive ions, then they come back with the same velocity. Why? Because positive ion is so big and electrons are very small. This is done in a collision in chapter number in class 11. All right. So this is what I have. N number of electrons, free electrons, they move in a random direction. So average velocity is going to be 0. Right. So what I take is I take I electron. Let's say I take I electrons, and I say I electrons having velocity Vi. Vi is the velocity of I electrons. Vi is the velocity of I electrons. I take a particular electron. And particular electrons having a velocity Vi. Particular electron having, and I say I is number that is 1, 2, 3, 4 up to n. I can go on up to this. So now if I don't apply electric fields, the electrons are in a random directions, right? Electron hits ions and then come back with the same velocity but in a random directions. Again I am repeating. Electron undergoing a collision with the ions and come back with the same velocity with different directions in a random direction. So therefore I say average velocity would be equal to what? Alright, 1 by n. This is how I find the average up to n. Vi is going to be 0. So therefore the average velocity is 0 and the net flow is 0. So that implies net flow is 0. Net flow is 0. So this is what I have. Alright. Move in a random directions after collisions, right? Let's say after collisions, right? So now what I write is electric field is not 0. Now electric field is not 0. Now I apply electric fields. When I apply electric field, every electron experiences electric force. Every electron experiences electric force. So the electric force is going to be minus EE. Why? Because the direction of electric fields and the direction of force are opposite. Therefore what I write minus E. Minus E refers to a force direction is opposite to electric field. Alright. So and then I say that F is equal to ma. Force is equal to mass into acceleration, right? Force is equal to mass into accelerations. Therefore, accelerations of electron is going to be this. This is acceleration of electrons. So, when electrons collide or hits positive ions, they'll come back with the same velocities and undergoing acceleration because of applied electric field. And how much acceleration? This much acceleration. This is the acceleration. This is the acceleration. Minus is that direction is opposite to electric fields. All right. Now what I'm going to do is electron undergoing acceleration until next collisions. Electrons keep accelerating until next collisions. All right. So I just say that. So I just say that at given time t is given time t, at given time t's, and the velocity of ith electron would be this is the velocity just after, immediately after collisions. This is the velocity immediately after collisions. Alright, this is the velocity immediately after, that is the same velocity, right? Then this is accelerations multiplied by Ti. Now, what is Ti? I said Ti is time between successive collisions. Ti is time between successive collisions. I told you just now, electron keep on accelerating until next collision. So this Ti is the time between successive collisions. So therefore, initially electron would have a velocity, that is the velocity just immediately after collisions, and then electron keep on accelerating and until next collisions. So this is the velocity. This is the velocity, right? So this Ti is the time between successive collisions. Ti is time. Now this is velocity at given time t. Alright, now I would like to find out average velocity of what we call as ith electrons. Now average velocity is going to be, now look at here. Now average velocity is going to be, now to find out average velocity after applying electric field E, look at here. There can be billions and billions of electrons. Alright. And every electron takes different intervals. Alright. That is what we call a random interval. Some electron may take more time between a collision. Some electron may take less time between a collisions. So I say the time interval between a collision is going to be different for different electrons. If I have a 10 billion electrons, there will be a 10 difference. But the difference is not that big, right? So therefore I say that average. So therefore what I am going to take is, I am going to take the average of this. I am going to take the average of this. And obviously I am going to take the average of this. Alright. So therefore average velocity is going to be, alright, average velocity is going to be average velocity immediately after collisions plus average time between successive collision. Average time between successive collision, right? So again this is going to be 0, random, right? So this way, this is going to be minus EE. Now what I'm going to do is this. This average is what we call as, this is relaxation times. This is what we call as relaxation times. Alright, relaxation times. Average time between successive collisions. Right? This is average time between successive collisions. Average time between successive collisions. Average time interval between successive collisions. Average time interval between the successive collisions. Now I take this average. Once I take this average, then I say this average velocity is what we call as drift velocity. This average velocity is what we call as drift velocities, which is going to be minus E and tau. This is the final expressions. This is what we call as a drift velocity. So because of an applied electric fields, entire free electrons moves with this velocity. So drift means movement because of some external force. Normally drift means the movements because of some external force, and that external force is nothing but an electric field, right? So this is what we call as drift velocity. This is what we call as drift velocity. All right. So look at here. When I say a drift velocity, when I say a drift velocity, this drift velocity is proportional to what? This drift velocity, I put modulus so that we get a vector quantity, a scalar quantity. Look at here. This drift velocity is proportional to electric field. Drift velocity is proportional to electric. If I apply more electric field, drift velocity is going to be more. If I apply less electric field, drift velocity is going to be less. This is how I relate between a drift velocity and electric fields. Alright. So now I just write here drift velocities minus E divided by M tau O drift velocity. Magnitude, this is what we call as magnitude of drift velocities is going to be this. Alright. Yeah. This is a drift velocity. Now this is the average velocity of free electrons under applied electric fields. If I don't apply electric field, there is no average velocity of free electrons. Alright. Now what I'm going to do is I take, this is what I'm going to take. So I say that in time intervals, delta t's, alright, every electron in a conductor moves, electron refers to a free electrons. Electron refer to a free electron. Every electron in a conductor moves a distance. What is the distance? Vd delta t. This is a distance moved. Alright, this is a distance moved. Now let's say I say that small n is a number density. Number density refers to a number of free electrons. Electrons per unit volumes. Alright. So look at here. Now this goes something like this. In a time interval delta t, alright, in a time interval delta t is number of free electrons find within this volume across this area. Alright, again, and this is a very important concept, right? I say, since in a time interval delta t, electrons move, electron moves, right? It moves the distance of Vd delta t. Alright, that means since this distance is Vd delta t, so in a time interval of delta t is all the free electrons within these volumes cross this area. So that means that tells the number of electrons crossing this area within time interval delta t. Alright. So this is, the reason is that this is a distance moved by every electrons. So again, I'm repeating, this is very, very important concept, right? So I say, first what I'm going to say is, in a time interval of delta t, every electron moves the distance of, average distance of Vd delta t. Now, since this distance is Vd delta t, alright, in a time interval of delta t, every free electrons within these volumes cross this area. And that means here again there is a electron, and then the electron in that side will replace these electrons. Electron in this side will replace that electrons. Alright, this is how it goes. Alright. So therefore therefore what I'm writing here is, a number of free electrons crossing area A, that is a cross-sectional area is crossing a cross-sectional area is cross-sectional area A in time delta t would be equal to n is number densities, and A is area, and this is distance. This is distance. This is going to be our distance. Look at here. This is going to be our distance. This is going to be our distance. This is going to be area, and total will become a volume, and n is number density. This become number of free electron crossing the cross-section area A in delta T. All right, this is what. Now what I'm going to do is, each electron carries minus E charge. All right. So now I say amount of charge crossing a cross-section area in time delta T would be equal to, minus E A. This is amount of charge. That charge is going to be this charge is going to be what? This charge is going to be negative charge. That is electron. This charge is going to be negative charge. All right, this charge is going to be negative. Now look at here. Negative charge goes in the direction opposite to electric field. Negative charge goes in the direction opposite to electric field. Now I say that amount of charge along electric field, let's say Q, that is Q would be equal to, I write here, electric field, that is Q would be equal to, and direction of electric field is opposite to the direction of electrons, so therefore I am going to put minus. Why minus here is direction of electric field is the direction of electron is opposite to the direction of electric field, therefore I put minus here. This minus is minus because of charge of electron is minus. Okay, then Vd, then delta T, this is minus is plus. This is the total charge. Now this is the total charge crossing a cross-sectional area. Now look at here, if I is current, if I is instantaneous currents, then delta T is a time intervals. Then the total charge would be equal to what? Total charge flowing across a cross-section area. Total charge flowing across a cross-section area is total charge flowing, I'll write here, across cross-sectional area, area A would be I delta T. All right. So now this I delta T is equal to EA Vd delta T. So delta T cancel out. This is what I have. Alright, this is how I relate between a current and dip velocity. Look at here. Now I can say the current is proportional to dip velocity. So in this topic, what we are trying to understand is finding out the relationship between dip velocity and electric field. Now relationship between a current and d velocity. So current is defined by d velocity, and d velocity is determined by electric field. This is how we relate every physical quantity. Alright. Now I am going to substitute a d velocity. This is again one important relation. So I'll put like this. Now I'll substitute this. I is equal to EA. What is d velocity? D velocity is E M. Alright, so I is equal to E square A electric field tau divided by L. Again, I guess this is what we have. Here we don't see electric field. Alright, now if I substitute the value of d velocity, I get the electric field. So electric current is also determined by electric field. This expression tells, right? Now I'll further do some simplification of. So I is a current. So I say a current divided by A, then E square, then E, time of relaxation is N. And what is that? What is I by A? We define I by A is current density. Previous class we defined current density. Alright, so current density is equal to I by A. Current density is equal to I by A. Current density is equal to I by A. So I just say J is equal to E square E divided by relaxations N. Okay. Now I would like to have these relations. We talk about Ohm's law. Alright, we say that E is equal to J. So we say that E is proportional to J, and this is resistivity. And we also say that this is proportional to J. Alright, this can be represented like 1 by, we can write like this. J is proportional to E, and J is equal to sigma E. We define this, right? And this is what we call as conductivity. So having this, now I just say this is equal to what is E? What is J? J is going to be E by rho E square E. E is a magnitude of electric field, right? So these two cancel out. Finally, I get this. Right, this tau divided by N. T square tau A, right? Where is N is missing, right? N is, I'm sorry, very sorry, N is missing here. Here N is missing. N is missing. N is missing. What else? There is N. Here is N. Here is N, right? So again here I have N, number density, number density, number density. Alright. So this is what I missed. N, and N is number density. Now finally I say rho is equal to N divided by N E square tau. This is the resistivity, and this is the origin of resistivity. Alright? And conductivity is what we define as N E square tau divided by N. So we found so many relationships. Alright. So that is why we say the resistivity is the nature of vectors. Alright. So this is the mass of electrons. This is the number densities. Number density is defined by the nature of material, right? And this is the charge of electrons that remains same. And this is the time of relaxations. And this quantity, the time of relaxation quantity, is determined by temperature. This is determined by temperature factors. Very important, later we will come across this. This time of relaxation is determined. So therefore, resistivity is defined by two important factors. One is the nature of material, that is N, number density. Another is the temperature, that is defined by time of relaxation. Alright. So now I have done a complete explanations regarding a drip velocity and relationship. Alright. So this is very important for exam, right? This is very important for exam. So this is what I have now. Alright. Relating a drip velocity and electric fields, and current and drip velocity, current and electric fields, and then I have a current density which we defines, and a current density and electric fields, and then later we found resistivity and then conductivity. Alright. Now next what I am going to do is mobility, right? So next what I am going to do is mobility. By mu. Very important again this. So this is what I am going to this talks about the mobility, means movement of, right? That means what about the mobility of free electrons? That means is it easily that means that is the free charge carrier can easily moved, or it's not that easily moved. Okay, so this is what we call a mobility. And I say we talk about in a day-to-day life. We say example like cycles. Mobility is little higher than a bike. Why? Because if I let a cycle to move on a plane in a particular slope, the movement of a cycle is more than a bike. Why? Because these factors like waves and rings. All right, these all factors. Right here we talk about mobility. That means we are excluding, right? We are going to exclude all the physical external factors, and we try to understand only the internal nature of particular object. That means whether it is cycles, or whether you are comparing cycles or the bike or truck, whatever. And here we are talking about free charge carrier, right? So therefore, when we talk about mobilities, this talks about look at here. Drip velocity is a movement because of applying. This is a movement because of what? Because of electric field. The external agent is electric fields. Now I told you just now we have to remove that external agency. How to remove external agents in physics or in mathematics? We are going to divide. All right. So therefore, mobility is what we define as drip velocities. This is defined as drip velocities, magnitude of drip velocities, per unit applied field. This is magnitude of drip velocity, ratio of magnitude of drip velocity to electric field. That is magnitude of drip velocity per unit applied electric fields. So this is what we had. This is the drip velocities divided by electric fields. This is what we have in mobility. Now, this is all nature of that particular material, right? So what is drip velocity? Drip velocity is defined as E tau divided by m divided by E, and E cancel out. Mobility is this. This is mobility. So look at here. Now when I talk about mobility, this E is a charge of electron. This is constant. This is constant. And this is a mass. A mass may vary. if I have a proton, mass is higher than electrons, and charge also vary, right? These are the factors that determines mobility, right? And then one more important factor is time of relaxations. Time of relaxations. Temperature factors, that is the time of relaxations, and then mass. Alright, that means if I apply same temperature for proton and an electron, which has more mobilities. So the electron will have more mobility than protons. Why? Because electron mass is almost like a 2000 times smaller than proton. So therefore, if I maintain temperature, that's therefore in physics we have to be everything in a control, right? I control the time of relaxations, and it is a proton and electron. I am comparing proton and electrons. Proton and electron would be having a same charge, then mass is going to be different. So therefore, this is how mobility varies. Alright, so if in exam, if you ask proton and electron under same temperature, which has more mobility, the straight answer is electron, which is having more mobility. Alright, this is all about mobility. Now the last part I'm going to discuss is the limitation of Ohm's law. Every theory has some limitations. Limitation means the theory could not able to explain. Alright, limiting up to what limit that theory could go. This is what we. Alright, when we talk about limitations, what is the limit of up to what limit this theory could able to explain a nature? Here in this case, nature is voltage and potential, or potential and current. Alright, this is what we talk about. Limitation means up to what limit the Ohm's law would able to explain the relationship between current and voltage. So these are the limitations. First limitation is yes, for any conductors, V is proportional to S. V is proportional to I up to certain currents. Up to certain currents. That means if you go on increasing voltage and current goes on increasing, after some time then the wire gets heats up. When the wire gets heats up, the resistance is going to increase. If a resistance changes, then it is no more Ohm's law. Ohm's law says the resistance is fixed. Alright. If a resistance changes, then the linearity is going to violate. You are going to violate the linearity, linear between voltage and current. Alright. So therefore, V ceases to be proportional to I. Alright. After some times. That means I can't go to a infinitely high current. If I make it very high currents, heating takes place and the resistance is going to change. This is one case. So up to this, Ohm's law is valid. Then if you go on, then you don't see. You see a curve. A curve is not going to be Ohm's law. Ohm's law means it has to be a straight. This is the first limitation. Very simple. Done in class 10 also. Second limitation is that the relationship between V and I depend on a sign. When you talk about Ohm's law, alright, this is a resistance. Whether I apply a voltage across this, or I apply voltage across this, it doesn't make any difference. Current doesn't change. Current across the resistance doesn't change by changing the sign of potential difference. However, for some electrical components, it is going to change, especially in case of PN junction diode. PN diode. This is what we found. So this diagram tells you that. So when you reverse the potentials, the variation of current differs from the variation of current in a previous case. So there is no fixed variation of currents. The variation of currents changes with changing potentials across electrical component. And this you are going to study detail in chapter number 14. Alright. Now this is one limitation, and the third limitation is that when you talk about Ohm's law, every voltage has particular current, or every voltage has particular current. If I increase the voltage, current is going to increase. That is, the relationship between voltage and currents are unique. Every voltage has a unique current. However, when we talk about germanium arsenide, this is a non-linear. This is a non-linearities, and then it's not unique. So look at here. I take this. I take this. You will be having current like this. So there will be having increase in the voltage and decrease in the voltage. Then I will be having one current. This is the one current at two different voltages. This is not valid in case of Ohm's law. Ohm's law says that every voltage gives rise a current, and that too increases linearly. Increases linear, and so this is not valid. So that means Ohm's law could not able to explain this. That means that Ohm's law could not able to explain this. So we need another law to explain this. This is what we are going to learn in maybe chapter 14, right? So with this, I have finished Ohm's law, limitation of Ohm's law, drift velocities. Okay, thank you.